Swayam Prabha. Digital India. Educated India.
Let me welcome you all for the next lecture on the inorganic chemistry of life, principles and perspectives. In the previous couple of classes, we have looked at the cobalt based enzymes. In the case of cobalt based enzymes, is particularly the coenzyme vitamin B12 is the one which acts associated with a large number of enzymes, and wherein we have seen group transfer, hydrate transfers, and reactions such as ribonucleotide reductase, all these kinds of things we have looked at. Now, let us take up another set of enzymes, the enzymes based on the nickel. Okay. So, let me draw your attention to the following slide, where we have a number of nickel enzymes have been given here. So, I have selected some enzymes where these are all working based on the nickel enzymes. These are urease, I will come into the details of these in a while, hydrogenase, carbon monoxide dehydrogenase, methyl coenzyme reductase, nickel superoxide dismutase, glyoxylase, cis trans isomerase, acetyl CoA synthase. Okay, so look at these reactions. I just wanted to draw your attention to one of the aspects in each of these reactions. So, each of these reactions, if you see very carefully, you would see some kind of a gaseous molecule either produced or utilized in the reaction of this. And you can see here the ammonia, you can see here hydrogen, you can see here CO2, you can see here methane, you can see here O2, and the only case that you do not see any gas is this particular one, which is glyoxylase and cis trans isomerase, etc. So, therefore, we can generally classify that the enzymes of nickel are primarily associated with either the utilization of the gas molecules or generating the gas molecules in this. So, having said that, now let us go through these reactions one by one. Urease reaction, urease is urea, ase means breaking. So, breaking the urea or hydrolyzing the urea. So, that is you can see that urea NH2CO NH2 with 2 equivalents of water giving rise to ammonia and the H2CO3. Okay. The hydrogenase is a kind of a reversible you have, that is protons are reduced to hydrogen gas and the hydrogen gas is oxidized to protons. So, the both ways that we have this kind of enzymes functioning. So, the reduced enzyme will function to reduce further, and the oxidase enzyme functions to oxidize further. So, therefore, H2 gas should be oxidized to H plus 2 electrons, and the H plus to be reduced to H plus 2 electrons to give to H2. Now, we also have another one, carbon monoxide dehydrogenase. So, dehydrogenase means removing the hydrogen. Removing the hydrogen is nothing but oxidation. So, CO dehydrogenase is nothing but an oxidative kind of a reaction, oxidative. So, how do we make out that? CO on the left side, whereas you have CO2 on the right side. So, the carbon is attached with one oxygen on the left side, carbon is attached to 2 oxygens. So, what is the formal oxidation state of the carbon monoxide C? So, you know oxygen is taken as 2 minus, then you will get the correspondingly 2 plus. On the other hand, if you take CO2 again neutral, there are 2 oxygens. So, 2 into 2 minus 4 minus. So, the carbon should be 4 plus. So, what has happened? Carbon monoxide, carbon center, which is 2 plus, goes to carbon dioxide, the carbon 4 plus. Okay. So, therefore, it is basically oxidation. So, in other words, carbon monoxide dehydrogenase is nothing but an oxidative kind of an enzyme. So, you take the other enzyme, methyl coenzyme M reductase. This is the coenzyme M. I am not showing the structure over here, a little later stage I will show that. And you have another center of the coenzyme. These two reacting together give the methane gas, and you have an oxidized form of those two, that will be reduced by another set of enzymes. So, we are not going into the details of that, but let us take it as granted that the methyl coenzyme is converted to its oxidized form with the methane gas. Okay, superoxide dismutase, nickel based. Why I wrote here nickel? Because we have already seen in the past superoxide dismutase. What are the other metal ions that we have seen? I am sure you will be able to recollect. Manganese case we have looked at, iron case we have looked at too. So, we have quite a few cases where superoxide dismutase is functioning, and we will be seeing in nickel now. We will also see in case of copper, which is bit differently functioning. Therefore, we are familiar with the reaction of the superoxide dismutase is superoxide is converted to hydrogen peroxide plus oxygen in this. Okay, go to the next enzyme here, glyoxylase. So, it is converting this kind of a structure, methyl glyoxal, to the pyruvic. Okay. So, therefore, you have two structures over there. So, you have the oxidative kind of a reaction going on, as you can see that. Cis trans isomerase. So, its title itself says it is an isomerization and it is a cis to trans. So, you can see here the two acetyl moieties, the carbonyls are oriented in the same direction. If you see on the right side, the carbonyl moieties are oriented in a different direction. So, that you have a cis here over here and the trans over there is giving a different kind of a structure. So, this also is carried out by nickel kind of an enzyme. So, the other reaction I have brought on this slide is that the acetyl coenzyme A synthase, that is A is the type A cluster, let us not worry too much about it. So, this shifted from CH3 CFESP using the other part of the coenzyme in presence of coenzyme this, it will go to the CH3 this. So, therefore, we have now seen a host of enzymes based on the nickel, where different kinds of reactions are happening. One of the reaction is hydrolysis reaction, other reaction is a redox reaction of the H2 to H plus kind of reaction, and then another oxidative reaction, carbon monoxide to carbon dioxide, all these several kinds of things that we have in the nickel. So, therefore, thus nickel is a very specialized special kind of an enzyme. How is it able to do that? We have already seen that except the glyoxylase, you have some kind of a gaseous molecule either utilized or generated in the reaction that we have seen. Other thing which is not seen here clearly, which you will see later on when we look at the mechanism, is that the nickel in these enzymes undergo a redox very facilely from nickel 2 either to oxidize form nickel 3 or the reduced form nickel 1. So, that means nickel 1, nickel 2 and nickel 3, these are the three kinds of things which are essential. Nickel case, nickel plus 1, nickel plus 2 and nickel plus 3. So, these are the three kinds of oxidation states, okay, and that is what is basically favoring all these kinds of reactions, and all this can be achieved within about 1.5 volts. So, the total thing can be achieved within 1.5 volts of the potential all these redox processes. So, that is very interesting. So, whatever I mentioned to you earlier, that you can see the same thing on this particular one, that is except the glyoxylase, you have all other enzymes are either producing the gas or utilizing the gas. I also mentioned to you there is a flexibility for the redox between +1, +2, +3 for nickel. Also there is a flexibility of the coordination. So, coordinating to different kinds of ligating centers as well as different coordination numbers as well. So, the coordination flexibility is the additional parameter that helps in this. This is coordination flexibility. Okay. And all this is possible within by changing the potential within about 1.5. So, the other thing which is not clear from the previous slide is that all these enzymes, do they have one nickel? Do they have more than one nickel? In fact, we have enzymes with one nickel, we also have enzymes with more than one nickel too, which you can see from the next slide. As you can see, start from the top left structure, which is a di-nickel center, go to the right, there is one nickel here, go to the further right, there is one nickel, one iron is a combined one, and there is another one iron which is not a nickel, but comes under the hydrogenase class, and you have a core structure with the iron and nickel being together form a specialized structure. You see that nickel over there, you see that nickel over there. So, now and you have a mononickel center here. So, you have a basically mononickel center, but it is a cluster with iron, and this is a mononickel center, this is a dinickel center, this is again mononickel center with some kind of a unit which looks like a porphyrin, but which is not a porphyrin, which is called the F430 factor, and then you have one nickel, one iron kind of things. So, now from this slide what do we understand? We understand that the nickel enzymes have either one nickel or two nickels or even nickel with some other kind of a ions like iron, and even in a cluster with a cluster. So, this kind of a cluster is reminiscent of what you have seen in the past. Where did you see such kind of a cluster? I am sure you can recollect that when I talked to you about the electron transfer by iron, which is called iron sulfur proteins, not by cytochromes, but iron sulfur proteins. There you have seen with 1 iron 1 sulfur, 2 iron 2 sulfur, 3 iron 3 sulfur, 3 iron 4 sulfur, 4 iron 4 sulfur. So, all these kind of clusters you have already seen, and you see one very similar where one of the additional unit is the nickel over here. So, now let us get back to these structures. This di-nickel center on the left top is the urease, which we have seen the reaction earlier. The second one is factor 4F30, which is present in the coenzyme M reductase, and these two are the hydrogenases. We will be discussing only this hydrogenase, but not this one. This is completely iron hydrogenase, and this is these two units are present in the enzyme called carbon monoxide dehydrogenase, and this is a site center which is present in the nickel superoxide dismutase. So, we will see details of quite a few of these systems in terms of their mechanistic aspects as we keep moving across that. Let us look at the first case. The first case is case on the nickel urease, the nickel containing urease. Okay. So, this can be seen from here. Nickel containing urease is that where you have the urea ended up with one ammonia with carbamate and then another ammonia and the H2CO3 carbonic acid. So, if you combine these two, what will happen? The urea combines with 2 moles of water, giving rise to 2 equivalents of ammonia and H2CO3. This is the total reaction. Why was this written in this way? This is written in this way because this reaction by the urease goes by 2-step process. In the first step, 1 ammonia is released, and the second step 1 more ammonia is released, and then the enzyme is regenerated back. Okay. So, that is precisely the reason why the reaction is shown over here, but if you want you can write the total reaction as well, no problem. Urea plus 2 water molecules giving 2 ammonia molecules plus H2CO3, absolutely fine, perfect. By writing this you get into yourself to understand the system much better. Now, let us look at the enzyme urease. Enzyme urease is not a small enzyme, it is a very huge enzyme. How do we say it is a huge enzyme? Number 1, you can see it has a 6 subunits, the alpha 2, beta 2, gamma 2. So, that is a alpha, beta, gamma twice. So, that means it is dimer of a tri subunit. Okay. So, trimeric subunit, dimer of that. So, and this has a huge molecular weight of about 600 kilodalton, and of course, there is a di-nickel center in each of these. So, there are 6 subunits and there are 6 dinuclear centers. That means the enzyme can function from each of its subunit. Now, if the one urea enters into one subunit, you will get 2 ammonia, one more urea enters into another subunit, you will get 2 more ammonias, like that. So, you have 6 subunits can consume 6 urea molecules and produce 12 ammonia molecules. So, you understand that there are 6 subunits and each of this has got a dinuclear center in each of this. So, now let us this whole protein is shown over here, as you can see from the colors. So, there is one part, there is another part, there is another part, 3. So, it is the 3 subunits, and you see above that, above this, above this. So, 3 more. So, each one is it's a dimer of a trimer. So, dimer of a trimer. So, the trimer is alpha, beta, gamma, the dimer is twice. So, therefore, totally you have all this. Okay. So, this is the enzyme. So, this is a very complex enzyme where you can have 6 moles of urea reacting and giving rise to 12 moles of ammonia. Now, if you look at as I said that each subunit has a dinuclear nickel center, then you can see that one here on the right side on the top. So, you would see there is one nickel here, you will see another nickel here. So, one of these nickel has got N2 here, nitrogen binding as one oxygen, another oxygen from carbonyl, other by water. So, what is this one? Nickel 1. So, what is the nickel 1 coordination? Nickel 1 coordination is 5. So, what are the 5 coordination geometries? 5 coordination geometries are generally trigonal bipyramidal or square pyramid. In this particular case, this is more of a square pyramid rather than of a trigonal bipyramid. Okay. So, this gives a N2O3 kind of a structure. So, this you have this structure is nickel N2O3. This is square pyramid. Okay, now look at the nickel. This is the nickel 1 center, and the other one you have on this side is the nickel 2, the nickel 2 center. So, this is the nickel 2, this is the nickel 2. The nickel 2 has got 6 connected atoms, of which again 2 are the nitrogens coming from the imidazoles or the histidines, and the remaining are coming from the oxygens, either the bridge oxygen or a water or a carboxylate or this carboxylate too, all kinds of things. So, you have, so therefore, the nickel 2 center is Ni N2O4, it is a octahedral. Of course, this is not a perfect octahedral and this is a distorted octahedral. So, and that is how it is. So, therefore, now you can see that the coordination flexibility in this itself, one of the nickel is the nickel with the 5 coordination, other nickel is with the nickel 6 coordination in these things. You see that? Okay. So, these are kinds of the things. Then what other things you can see from here? there is one other interesting feature. The two nickels are not separated, but connected by a bridge. So, the bridging group over there could be water, hydroxyl, etc. So, this is a connected bridge from these between these two. So, therefore, we have two distinct coordinatively two distinct nickels. So, therefore, we can think each one of these could be useful one different kind of a function that we will learn in just in a while very soon. Now, in the next couple of slides we will try to understand this. Okay. So, so you have the oxygens coming from carboxylic groups, nitrogens coming from imidazoles, oxygen coming from water, all these kinds of things, and the bridging. Let us look at this idea about this particular urease mechanistic aspects. Next 3 to 4 slides we will try to understand how this urea is finally cleaved to ammonia and H2CO3. Before going to that, let us look at this is an enzyme with a nickel 2 plus, and in this enzyme there is no redox. None of the nickel undergoes any reduction or oxidation. That means both the nickels stay in +2 state all through. Point number 1. Number 2, if you see urea, if you put in water, there will be some amount of hydrolysis, that will be very slow kind of thing. But in presence of the urease enzyme, if you put urease in that, the reaction goes very fast. Okay. So, it's the K catalysis is around 3000 second inverse, and the K cat by Km is 10 power 6 mole inverse second inverse. So, therefore, the enzyme gives a very high fold of enhancement, which is about 10 power 14 fold reaction rate as compared to the reaction of urease without enzyme. You just take the urea, put into the water, you take the urea in water, but put urease enzyme. So, these are the two differences that it tells. So, this particular sentence explains you that the reaction of the hydrolysis reaction of the urea is expedited by 10 power 14. You know, 10 power 14 is a huge number, 10 power 6 is million and 10 power 9 is billion. It is almost like a billion millions kind of thing. So, huge, that is what is the reaction rates that you are looking at. Now, let us get into the ourselves into the reaction aspects of it. How does it do the thing? Now, for this I have shown some structures on this side. I will draw your attention as and when is required, and we can try to understand this one. Okay. So, we take these two dark spots as the nickel 1 and nickel 2 center, and when the urea approaches the nickel this enzyme, it is directed towards the this particular region is called the catalytic site, where the nickel centers are there, and that is directed towards this, because there is some of the protein moieties which are now you can see as covering, they are opening, they are in an open form. So, when they are away, this is called a flap open, the urea can enter in and then bind through. Once it comes, it binds through the carbonyl moiety. So, once it binds the carbonyl moiety, these residues which were open earlier, this residue, this residue, this residue, these are all open which were earlier in an enzyme before substrate exposure, they are turned, they twist their carbonyls towards this particular thing, and then flap is closed. So, now urea has come, urea initially interacts through the carbonyl through the one of the nickel center, and now this particular urea is now held like a kind of a prisoner inside this. So, you can see this is kind of a prison chamber which is counted. So, earlier all these residues are opened up, and when the urea comes and binds, they are closed. So, therefore, this kind of a closing will make the recognition of the urea by the enzyme 2. So, how does this recognition works? This recognition works when it flap closes, these hydrogens, you can see that the NH etc., etc., All of these NHS are stabilized by the hydrogen bonding. Okay. So, you can see there is a hydrogen bonding stabilization coming from all of these. And you can also see there is an NH from the histidine. This proton can transfer when this CN bond is ready to cleave. When the CN bond is ready to cleave, then you can basically talk about the protonation. In other words, the proton push towards this will expedite this particular nucleophilic attack. So, that is we have looked at one kind of a nickel center. Then on the neighbor nickel center, you can see that the water which is activated, and becomes the OH. And you know, nickel bound OH is a base, is a nucleophile, can give an attack at the CO, which is an electrophilic center which is present in the urea. So, that attack will form an intermediate of this kind. You see that? So, now you can see the urea molecule once binds the CO is recognized by all these hydrogen bonds. I will tell the details in the later slides, but now take it as granted that there is a lot of hydrogen bonding interactions are going through this, and this attack of the OH, a nickel bound OH of the second nickel would give you an intermediate to this. And this, when the proton is transferred from this imidazole to the nitrogen center, that will favor the cleavage of the NC bond and will come to the one side will come as ammonia, other side will come as the NH2HCO2 or NH2COOH. Okay. So, this will be now comes into the picture of NH2COO. So, now you have a urea molecule, urea binding through CO, group, and then locked in the active site through hydrogen bonds. So, that is what all you have seen. And then you have also seen that the proton from the nearby histidine can facilitate the reaction of the cleavage of this. So, as a result of that, so you will find, so now urea, and this is the urea, you have NH2s and NH2s of this kind, and this will get the other hydrogen, okay, and this will have the OH from the other nickel makes this, okay, and now this is at the electrophilic center, and that will cleave this bond, and that will give you an NH3, and it will give COOH and NH2. So, this is bound to protein, this is bound to protein, and this is further. So, this is the intermediate step. Now, when this particular intermediate step is exposed to water, then the further cleavage will occur, which I will explain to you in the next slide on this. Okay. So, this is the intermediate step that I have shown you earlier. Okay. So, now looking at the next slide, so you can see that the whole thing is, we can try to recollect this. The urease enzyme, in presence of the urea, it acts on the urea and generates 1 mole of the ammonia and generates an intermediate of the carbamate. This upon further water reaction will again give back to ammonia and the H2CO3, or in full water, if it is only one water molecule, then you have the CO2 and then this will reverse back to that. Now, this whole thing is explained by a mechanistic path over here. In the mechanistic path over here, then you can see that the urea, I have given two sets of mechanistic paths, where center part written as A in this side and the center part is written B here. So, you start from enzyme and then you go to the next, and then things of this kind go back to this. So, this is the one cycle. The other is go to this intermediate and to the next one, to the next one and to the next one and go back to this. Okay. So, this is a kind of a thing, and in the next class I will give all the details of this particular enzyme, how it binds. I have already mentioned certain points of it, how it breaks by showing the structures of all these via the mechanistic aspect, and further highlight the other features. There is some sulfhydryl function, how that sulfhydryl function also helps in the reactivity of this. So, all this I will explain you in the next class. Thank you very much.